You should.
But can you reduce this yourself? Maybe I should.
Yeah.
Welcome to this seminar, exceptionally on Friday, because Fabien is only available on Friday for some reason. And our guest is Fabien Roquet, and he's a professor in Gothenburg, in Sweden, since for a year, because before that he was in Stockholm University. But can already recognize from his name that he's French, and he studied in Paris, right? Graduated with PhD in Paris also, in one of the 12 universities I learned yesterday. And then he became MIT guy, right? He went to Boston, to the MIT, to work with Carl Wunsch. After he went to Stockholm, and now he became professor in Gothenburg, and he's working on all kinds of interesting questions, in particular on the nonlinear equation of state. And this is something which he wants to present now, right? So
yeah, exactly. So I wanted to be here today because it's Friday the 13th, so I thought it would be a lucky day. So I'm going to talk about nonlinearities of the equation of state of seawater, and I'm going to claim that there are the properties of the equation of state is in fact central to the generation maintenance of a polar halocline, which then is a condition for sea ice formation. So I will explain what I mean by that. But then first a bit of context. So I'm sure you're all well aware of that. So the equation of state is a relation that gives density as a function of temperature, salinity, and pressure. And it is nonlinear in the sense that if you would increase, say, by 1 degree the temperature of a water parcel, the change in density will not be the same depending on the temperature of that water parcel. In fact, warm water will have a change in density that will be greater than a cold temperature. And we will see that it will be absolutely central to the argument. Here you can see TA's diagram with the isopycnals. And one thing of interest is you see that, so the slope of this isopycnals, which is in fact the ratio between the thermal expansion coefficient and the high-line contraction coefficient, varies depending on where you are in the space, in the temperature salinity space, but also varies with pressure. So if you look at the contours of density at 4 kilometers of depth, you see that they have a different slope, and that in fact is related to this thermobaric effect, the fact that again the property of the equation of state varies with pressure. Of course, if you have any question at any stage, please don't hesitate to ask. So there are some.
Okay, you can use a stick if you want. There's one in the corner. I think this pointer nobody can see.
Yes, but the audience should see the pointer as well if you press the button. Yeah.
Okay. So yeah, there are two very well-known and discussed effects of the nonlinearity of the equation of state. So I want to mention them, although they won't be central to this talk. There's cabbeling. So cabbeling is the fact that if you mix two water masses that say would have same density, but yet not same temperature, the resulting water will be denser than the original water. So that's cabbeling. The name, in fact, comes from German, Kabel. It was an old theory that water would be pulled together just like if there was a cable between water mass. And that's just to refer to the convergence of that is generated by this effect. Thermobaricity, it's it does have a similar property. Now it is where the fact that the variation of density with temperature varies differently depending on at which pressure you are, and so that can create very interesting effects. So again, yeah, this has been studied, and that's very interesting field, but that will not be the center of this talk. So there's been some work about the sensitivity of the ocean circulation to the equation of state that were based mostly on like global models with like a forced ocean conditions, prescribed forcing. And this study I've showed already, so we know it, that the dependence of the thermal expansion coefficient with respect to both temperature and pressure, and those dependents are the key ingredients for cabelling and for thermobaricity. They are actually key to explaining the observed stratification. So here you have results of such experiments. So you have a section of temperature, so zonal mean, meridional section. So here is using the actual equation of state for seawater, so the full nonlinear one. So you recognize here, so the warm thermocline and the cold Antarctic bottom water that are originating from the high latitudes. So this is quite realistic if you compare to observations in the ocean. And then running the same model, but just now changing the equation of state. So instead of having the full nonlinear equation of state, plug a linear equation of state instead. So linear means that now the thermal expansion coefficient is made constant. Well, if you compare the distribution of temperature, you see that there are things that have changed, and most importantly, the bottom is now much colder. So in fact, on average, the ocean that you generate in that way is 2 degrees colder in that linear case than in the reference case. And in fact, this one compares favorably with this one. This one is a run where there's a simplified equation of states. We just capture but in a simplest way, the dependence of the thermal expansion coefficient with both temperature and pressure by having a linear variation with respect to these two quantities. And then, in fact, we are able to recover a very realistic structure of the ocean. So that shows, this study showed that those nonlinear effects are important. You cannot ignore them if you want to represent the stratification of the ocean. But you can capture their bulk effects in a very simple way at the same time.
Okay. Can you explain again the simple way? The simple you have.
So simple way in the sense that you will have an equation with just 4 or 5 terms. So the thermal expansion coefficient now is varying linearly with both temperature and pressure. And so when you look at your equation of state, then you will have the density will have a quadratic term in the temperature, a term that varies the product temperature pressure, and then one linear term for the salinity, and that's it. That's as simple as you can do while retaining nonlinearity, and that's enough to represent the bulk of those effects that we find in the ocean. One interesting point also that was made in this paper was that I was able to recover the best comparison between this simplified nonlinear equation and the realistic one, if I was specifically making sure that the value of the thermal expansion coefficient at the freezing point would be equal to the realistic one, the one that we have in the real equation of state. So that indicated already that there is a particular sensitivity of the stratification to the equation of state right at the freezing point. For cold temperature, there is something more important than for any other place in the TS range. Okay? So one key to understand this is to talk about stratification control. So it's to analyze what determines the stratification that we observe. Is it more temperature or is it more salinity? So here you have the stratification in the upper 500 meter based on the climatology. So, and obtained as just the difference in potential density between 500 meter and the surface. And you can actually decompose this into the sum of two contributions, one coming from temperature and one coming from salinity. And just visually, you can see here already that in subtropics and tropical regions, temperature is dominant in setting the stratification. While in a high latitude ocean, you can see in the Arctic, but also in the Southern Ocean, that there the stratification that we observe comes from the salinity variation mostly. And in the subtropics, you can see something that's very well known is that salinity contribution is negative. So the salinity variation is weakening the stratification. It's acting against the dominant stratification set by the temperature contrast. Okay, and so when you look at what these terms depend on, interestingly, so this is here the contribution from temperature and here from salinity. And each of these terms is scaled by here alpha and beta. So alpha is the thermal expansion coefficient and beta is the high-end contraction coefficient. So here you see a possibility of a direct impact of the thermal expansion coefficient, which derives from the equation of state, on the stratification control. Namely, if the thermal expansion coefficient is larger, you expect temperature to have more potential to dominate the stratification and vice versa, right? So with this context given, I will now present, so in three parts, I hope I will have time to go up to the end. So first, I will spend some time discussing how the thermal expansion coefficient vary in the ocean and why. So I will go back into some fundamental water chemistry, just briefly, that you get some interesting concepts about this, because those variations are very unique to water. There's not many chemical fluid, not many fluids that have such strange properties. And then in the second part, we will discuss the sensitivity of sea ice cover to change in the thermal expansion coefficient value in a coupled climate model. And that's where I will claim then what I said in the title, that this variation is central to allow the formation of sea ice. And then finally, I will come back to this concept of stratification control and how it can be related with the surface buoyancy forcing. Okay, so some very basic water chemistry. So if you take pure water, it has a very strange property, is that the maximum density is not reached at the freezing point. So this is density here as a function of temperature. The maximum density is actually reached at 4 degrees Celsius, around 4 degrees, instead of being reached at the freezing point, which is at 0 degree. So what that means is that density increase with temperature below 4 degrees. Okay, so that takes a bit of time to think about it. So you're warming water. When you're warming, usually you expect expansion. That's what you get most of the time. But this time, density increase, so that means that you will have contraction of your water as you warm it. This is very strange in that sense. And so when you're right at 4 degrees, you have a plateau, and then you get back to a more typical, more expected behavior that you warm your water, it expands, its density decrease, right? So in terms of thermal expansion coefficient, that is defined here as minus the relative variation of density with temperature. What it means is that this coefficient alpha is now negative below 4 degrees. Okay, so it changed sign at 4 degrees. And yeah, in a usual fluid, alpha is positive and actually well positive, quite far from 0. But here it does cross 0, and there is a regime in which it is negative. So to understand how that is possible, you have to go back.
Move the dashed line at the top.
The dashed line, so it represents basically what you would expect from a normal fluid. Okay, in that paper, so of course it's approximately defined, but that's basically what you would expect with a normal fluid, where basically alpha varies very little with temperature. And then when it changes phase, density increase. While water, not only, yeah, I should have said that actually, not only as you cool water below 4 degrees, the density decrease, but when it freezes, the density decrease even more. Okay, so ice is lighter than water, and that's why ice floats actually, which is also a very unusual property for a substance. So yeah, to understand how that is possible, you have to go back to basics about the molecular structure of water, and the fact in particular that water molecules have a polarity. So you have this atom of oxygen surrounded by 2 atoms of hydrogen, and there is an angle between, so HOH, which is around 104.5 degrees. And because you have these 2 protons on that side of your molecule, then you have 2 sides on the other side, which are relatively negative in charge. Yeah, this is here, if you want, some sort of accumulation of positive charge, and so negative charge on the other side. And that creates these sites here that can form so-called hydrogen bonds. So there are several molecules that can do that. So water is one of the most efficient to produce hydrogen bonds, which are weaker than usual chemical bonds. But that are strong enough that they can retain molecules of water close to each other for some time. And so there's a natural tendency for water molecules to form a tetrahedron like this. So with one water molecule at the center of 1, 2, 3, 4 molecules, okay, which are linked together by those hydrogen bonds. And the key here, and that's what makes water so peculiar, is that this tetrahedron is almost perfect because the angle HOH is very similar to the one you would require in the geometrical figure of a tetrahedron. Okay, so this is a very stable structure. And that's in fact ice. When you look at the ice that is formed at atmospheric pressure, it does have this sort of crystal structure held in place by those hydrogen bonds. And in fact, there's almost enough space to put a water molecule inside those hexagons, which means that this structure is not dense, is much less dense than if you had water molecules being randomly distributed. And that is why ice is lighter than liquid water near the freezing point. But that's also for the same reason that water decreases density when it gets closer to the freezing point, because there you will find more and more of these low density clusters. And so as it cools down, it starts to form more and more of these structures in a so-called mixture model. And this is therefore why the thermal expansion coefficient is able to be negative, because as you cool down, instead of making molecules closer, you're actually forming these crystals that will hold molecules apart, right?
Are the crystals the same as the tetrahedron?
Yes, except these are not stable structure. It's more like metastable, and on average they are there. There are clusters, but this is very dynamic, of course. But the important part is that there is an increasing proportion of water molecules arranged in those kind of clusters as you go colder. This is subject of active research. In fact, it's quite one of the collaborator I work with is a specialist of water chemistry, and their best model of water is actually freezing at -70 degrees, so, which is a bit cold. So they have a big issue even to represent the most basic properties of water in a model. So it is a very complex problem. So because of this property, we have in lakes that are cold enough this strange property that they mix at 2 seasons, and that they are always filled with this 4-degree densest water at the bottom. And this here, which is colder at the surface than at the bottom, and that will help to form ice eventually, if it's cold enough. It is stable because even if it's colder, it's lighter, right? But we don't have this in the ocean. In fact, in the ocean, the fact we add salt. So here, if you have the thermal expansion coefficient as a function of salinity, so at 0 salinity, that's pure water, we find what we have seen before. So the maximum density is at 4 degrees, and then density decreases as you get to the freezing point. But as you add salt, you lose that property. So beyond around 25 grams per kilogram, now the maximum density is reached at the freezing point. So that's a maximum density that is warmer than the freezing point. This is only for brackish water or very low salinity waters. And so you see that there is a similar trend, by the way. If you increase pressure, so here depth, you do find also that the freezing point is lowered, and that the maximum density gets closer and closer to the freezing point until it vanish, the speculative vanish. And interestingly, you see that there is an equivalence in the effect that an increase of pressure of 2000 meters or an increase of salinity of 20 grams per kilogram may have on the property of seawater. But so you see in the ocean, in most of the ocean, seawater is salty enough that you don't have this maximum density. So you may say then, so that this effect is not there, so it's probably not so important, and you can move on. And I think that's been the main, the usual assumption, that those effects are not so important for the ocean because salt is removing that maximum density. But still, when you look at the distribution of thermal expansion coefficient in the ocean, so this is at the surface here based on the climatology. What's very interesting is that it does vary a lot. So in fact, at the freezing point, it is 0.3 10 to the minus 4 per Kelvin. While when you're in the tropical region, we are above 0.3 10 to the minus 3. So it's 1 order of magnitude larger. So even though the thermal expansion coefficient never gets negative in most of the ocean, it gets very small near the freezing point. And so you have large relative variation of the thermal expansion coefficient. And so the question is, can this affect large-scale property of the ocean? So I get to the second part on sea ice. So what we did, so this is a work with several collaborators, and in particular with David Ferreira from the Reading University. He has this very nice configuration called the Aqua Planet, where you have a fully coupled ocean atmosphere model on a pretty coarse grid, but it's the full primitive equation that are being solved. And the goal is to try to assess what is most fundamental about the climate. So what do you need to the minimum to produce the key elements that makes our climate system? So it's very interesting work being done with this model. And here we use a configuration called double Drake, where in the ocean, you just have two ridges that goes up to the surface, up to the pole, North Pole. Okay, so one would be basically your European African continent, and one would be your American continent. So that will create some sort of Atlantic basin and Pacific basin on the other side, right? And we have added, we have made a few modifications in the south as well to have a pretty realistic, or as realistic as it could get, formation of bottom water in the Southern Ocean. So to try to have a substantial overturning by adding mid-depth ridge that goes from this pseudo-American continent right to the South Pole. So of course, this is not the at all close to the real Earth, but it does retain the most fundamental geometrical constraint in the system, that you can start to see the major feature of the atmospheric circulation and of the oceanic circulation, and in particular that this configuration will produce convection only in the pseudo-Atlantic basin in the north, and another source of convection below the sea ice in the southern part of the basin. Okay, so then we took this model and we play with the equation of state. We made it linear, so we used a constant value for the thermal expansion coefficient. And we tested different value of this alpha value. And so the result here, the most striking result is given in this plot here as a function of alpha, the thermal expansion coefficient. So each blue dot is one equilibrium state of the model for the given alpha value. And the red value here, so it's the total sea ice cover in the model when you use the real equation of state, the fully nonlinear equation of state. So you see there is some permanent sea ice in the model. But now you see that as you modify the value of alpha, make it larger and larger, you do have a decline in a sea ice area and even a complete disappearance of sea ice if you exceed a certain threshold in your thermal expansion coefficient. Okay, so that was a very striking result that I will now try to explain. So you can have some sort of simple argument to understand why that would be, why the amount of sea ice that you produce may vary depending on the value of alpha. So you can have a simple argument based on a 1D model, the one that Martinson proposed, below sea ice. So it's a model where you assume that the mixed layer is at the freezing point. You consider different surface fluxes. You will have some feedbacks as you create or make ice that will have effect on the salinity. And there is then some entrainment at the bottom of the layer. And I will not get into the details, but the key point is that if you assume that the surface buoyancy forcing should be on average positive to maintain year-long stability of your mixed layer, then you find that that can happen only if alpha is less than a certain critical value of thermal expansion coefficient, which itself will be a function of the precipitation at the surface that bring fresh water and stabilize your mixed layer, and the heat flux at the surface, Q, which is the cooling, that destabilize. And there is an extra term here that has to do with the melting or the formation of sea ice. Okay, so Li here is the latent heat of fusion. And so if you plug some numbers into this very simple expression, you find that you expect a critical threshold for your thermal expansion coefficient of around 0.9 10 to the minus 4 per Kelvin, which is not that far from the value that we got. You see that here our critical threshold would be rather at 1.2 10 to the minus 4, so it's slightly larger. But of course, this little theory is oversimplistic, so we are not expecting an exact match. What's really important to realize here, in any case, is that this value is much smaller than the average value of thermal expansion in water. In fact, on average, the thermal expansion coefficient in the ocean is twice this value. And it can be up to 3 times bigger than this value. So here what we see is that if the water did not have this funny property that is thermal expansion coefficient decrease at low temperature, we would not be able to maintain stability of the mixed layer in polar regions. We would not be able to maintain the halocline. That is a condition for the sea ice formation. Instead, in winter, the cooling would destroy any convection, and so you would have deep convection occurring on large parts of the ocean. So in that sense, the fact that there is relatively minor vertical exchange between the surface and the bottom of the ocean in polar region is in a large part due to this funny property of water. Okay, that's kind of helping salt to shield the surface from the bottom of the ocean in polar regions and prevent convection to occur too much. So here you have some more detailed plots. I will not get too much into details, but just to say, so here you have in red is the bottom temperature as a function of alpha. So you see that as alpha increase, you don't get any sea ice, but instead you will get very cold ocean because there's a lot more convection occurring. And you can see that in this case, so there is no sea ice, there is no blue line here. So that simulation, this is the temperature section and the salinity section. There is no sea ice, and at the same time, it is much colder than any other. So you see the bottom here for the control run is around 4 to 5 degrees. Here we are below 4 degrees. If you have a low value of alpha and therefore a lot of sea ice that can be maintained, now the bottom of the ocean is in fact more than 10 degrees of temperature. So it's very warm. And in fact, when you look at the convection in this simulation, there's very little convection occurring anywhere. And most of it is being driven by freshwater net flux. So it is through evaporation that you are able to convect, mostly in the subtropics. So it's a very different world. Okay. Of course, I'm not saying that we would ever reach this kind of scenario on Earth. I mean, the equation of state is what it is, but it's just to illustrate how this variation of thermal expansion coefficient, how fundamental an effect it has on the stratification. Yes?
One question, what would be, instead of the art simulations, what would be the linear case for thermal expansion coefficient? Where would it be in between?
What would be
instead of the art simulations, when you assume a constant thermal expansion coefficient, what do people agree on? Which coefficient are they using?
Well, they're using the.
It's not so easy to.
No, I mean, in reality, it varies. We use the standard nowadays is called TRR181, the thermodynamic equation of state, that gives you density and that gives you all the derived quantities from there, including thermal expansion coefficient. And so, in that case, in the real ocean, you would get something. So of course, in the aquaplanet, it won't be exactly that, but you will definitely get something where the thermal expansion coefficient at the surface is pretty much proportional to the surface temperature and varies from a relatively large value in the tropics with the maximum value where it's warmest up to values that are very small in polar seas, which is smallest at the freezing point. So right where sea ice is being formed. Okay, that's the form, and thermal expansion coefficient is itself very well known, a function of temperature, salinity, and pressure. That's a property of water. So as long as the ocean is made of water, we always get the same equation of state. And we know it very well from laboratory experiments. So there is no uncertainty about this coefficient and about the fact about how it is represented in models. What here I want to emphasize is the fact that it varies and that it varies proportionally to temperature, how fundamental an effect it can have on the stratification. Okay. I hope I answer your question.
Yes.
Good. Okay, so let's continue. Here, what you can see is the stratification. So the solid line is the stratification due to the temperature, and the dashed line is the stratification due to salinity. So the formulas are given here. And those values are integrated from surface to bottom. And so the color will tell you the different runs. So the blue is the control run, so which looks very similar to what we observe in the real ocean, where you have stratification dominated by temperature in the subtropics. The salinity becomes dominant in the high latitudes. And the temperature stratification is negative in the high latitude, especially in the Southern Ocean, meaning that temperature is destabilizing your stratification. And that is another way to say that it is colder at the surface than at the bottom. But now if you look at the different runs, so one with a lot of sea ice here controlled massively by salinity, you can check that indeed salinity has a dominant effect now in a much larger region. And even in the tropics, it remains positive. So everywhere it is stratified in salt. And temperature now is dominant only on a very limited tropical region. If, in contrast, you look at the most extreme case where now alpha value is very large, there's no sea ice. Now temperature is extremely dominant everywhere. You can see that temperature stratification is large everywhere, is positive everywhere, and there is no salinity stratification, almost no, that can be maintained in the sea ice forming regions, okay? And if you take the relative ratio between these two, that's a number that I call the stratification control index that tells you which one of the temperature of salinity stratification is dominant. So when that index is more than 1, that means that you are controlled in temperature, stratification is dominated by temperature, and that salinity is weakening the stratification, so it is opposing the stratification. When you're below -1, that's the opposite. Now the salinity dominates stratification and temperature is negative, is destabilizing. And then you have this intermediate effect between -1 and 1, where now both temperature and salinity are stabilizing. And you can see, so the control run is the blue line again. So you go from strongly salinity dominant to strongly temperature dominant in the subtropics. Now, as you increase the value of alpha, keeping it constant in these 3 different runs, you see that the stratification control index increase at all latitudes. Okay, so you have here a clear proof that the simple value of alpha will determine which of temperature salinity will be more effective at dominating the stratification. And interestingly, you see that when the value of alpha in the realistic run, in the control run, correspond to the value at a given latitude of a given run, they actually have very similar stratification control index. So it seems to be quite locally controlled. If in a given place you have a given value of alpha, you will find a certain sort of stratification. So alpha is as very powerful, gives a very powerful constraint on the stratification that you obtain. That's the key message I want to hammer. Okay, so a bit of time left for the last part. Let's look now at the stratification control index in the actual ocean. So here, estimated using the ECHO solution. We have done it also with real observation, and we get something quite similar. We do find, so when it's red, it's above 1, so that means it's dominated by temperature. That's what we call an alpha region, following the terminology proposed by Carmack. When it's blue, it means that it's controlled by salinity, and that's what we call a beta region. And you do see that for the most part, subtropics and tropics are alpha regions, and there is a transition zone toward beta region when you go sufficiently poleward, okay? You do see that this transition zone is in fact in a place where there's a lot of ventilation that we observe. It is these regions are known to be active. And so we see here an interesting perspective that these regions of transition may be related to the type of stratification that you are able to maintain, and therefore to the fact that the alpha value cross a certain threshold in those regions, making salinity more dominant because temperature decrease. So there is this nonlinear feedback between temperature decrease and then promote salinity as a dominating the stratification. And so with my PhD student, Romain Canet, that was that was the fundamental question that we asked for his PhD: what sets the position of the polar transition zone? So he's still doing the PhD. So I will just present some of his work now. Well, that I've forgotten about this, but maybe we can go directly to Romain's work. So he set up an idealized configuration with a square basin, which is symmetric at the equator. So it's in effect a basin going symmetrically north and south, and prescribe temperature relaxation toward this profile here with a bit of seasonal variation, prescribe salinity profile, and also some wind stress. So those values are chosen to correspond to normal condition in the North Atlantic. And then running the model with equation of states that are kept nonlinear, but tweaking the different parameters. So in particular, to make the alpha value vary more or less with temperature, and making it also more or less large at low temperature near the freezing point. And what we obtain is that doing many runs, there's something that was found very robust, is that as you increase the value of the thermal expansion coefficient near the freezing point, the position of the transition that is now given with this green dash line is migrating northward. So here it shows that the position of the polar transition zone depends largely, so can be affected a lot by changing this polar TEC value. And why is that? Is because, and that's what you can see with the colors behind, these colors gives you the buoyancy flux. And you see the white line here is where the buoyancy flux change sign, the year mean buoyancy flux change sign. And so we find that this buoyancy flux change sign at a position increasingly poleward following the transition zone. And this migration of the place where buoyancy flux change sign is related directly to the thermal expansion coefficient that we have through what we described, that as this value get larger, then the fresh water has less and less potential to maintain the stratification. Okay. And I should say that all of these runs are done with exactly the same wind stress. Okay, we don't vary wind and still get first order variation in the position and structure of our transition zone. So this is strongly, and that's the conclusion of that paper that just got accepted, is that the position of the polar transition zone is mostly determined by the place where the buoyancy flux change sign. Now, this is some preliminary work that he has been doing, and I will finish with that. So trying to see if we find something similar in the real ocean. Here again, you have estimated using observations in the EN4 database, gridded spatially. So we have computed the climatology of the stratification control index. So you do find again this transition from red to blue, from temperature dominated towards stratification dominated. And what you can see, places which are hatched are where the buoyancy flux is positive, is stabilizing, and in a year mean sense, and where it's not hatched, it's when it's negative, so where it's destabilizing. And you do find a pretty good match between the position of the transition zones seen as the transition from alpha to beta region and the position where you change the sign of your buoyancy flux. Okay, so it's preliminary, but already we interpret that as confirmation that there's this tight link between these two features. And if you look at the mixed layer depth, you find exactly like he found in his idealized models, that the place where the mixed layer is deepest is found immediately equatorward of the place where buoyancy change sign, and where, so right within the transition zone. So the ventilation is located exactly where you change sign, and reminding you that this is strongly affected by the temperature through its effect on the thermal expansion coefficient. Okay? So that can have also consequence on how we may think about climate change, how it can affect stratification. You see that here we find a process an additional process that makes stratification vary heavily depending on the surface temperature. And I will finish with a few conclusions. So the main effect of the nonlinearity of the equation of states. So we have seen that it is related to variation of the thermal expansion coefficient, and especially its variation as a function of temperature. The fact it decreases at low temperature. That decrease at low temperature greatly facilitates the formation of the polar halocline, itself a condition for sea ice formation. And finally, the position of the polar transition zone is found to be related to the change of sign in sign of the surface buoyancy flux. And due to the fact that freshwater flux becomes more and more dominant as you get into colder regions. So that means another way to say that the main nonlinear effect of the equation of states, in fact, reside in the way it modulates the buoyancy forcing. And again, the drop in the value of TEC facilitates greatly this transition. And here I just remind the paper that has been published. If you're interested, have a look at it, and another paper in preparation. Yeah, thank you very much. That's it for today.
Not for this talk. Are there any questions from the audience here? Yeah.